Okay, hi everyone, and welcome back to the Cubical set seminar at the MSRI. And today we have a great pleasure of having Emily Riehl, who will speak about the equivariant uniform confibration model of cubical homotopy type theory.
Okay, yeah, thanks a lot. It's a pleasure to have an opportunity to speak. So this is joint work from last summer with Steve Awaday, Evan Cavallo, Thierry Cocan, and Christian Settler that mostly took place at the Center for Advanced Study in Oslo. And I haven't really thought about this project since August, which is not such a good thing because it means the paper is still not available. And also I'm going to be a little bit rusty on some of the details that were like very precise in my head a while ago. I should give a shout out before we begin to Ulrich Buchholz. I've spoken about this once before, and so of course I have notes, but these notes are in my office, and my office is in a state which is currently under shelter-in-place order, so I wasn't able to get anybody to get into my office and get my notes so I could use them to prepare this talk. But Ulrich was at the talk that I gave once before and documented it with this like remarkable Facebook thread that included a lot of Blackboard photos and kind of a line by line summary of basically everything I said. So when preparing this talk, I logged onto Facebook, downloaded all of his photos, and then kind of re-prepared from there. So thanks, Ulrich, for reminding me what I understood at one point. Okay, so what I've decided, as I was talking with Chris before we started recording, I don't know if you're having this experience, but I'm finding it very hard to focus on these Zoom talks. So rather than be like massively comprehensive, I'm going to try and just kind of give you an overview of this project and draw your attention to some of the ideas that I find most interesting and kind of skip over details in any attempt to be comprehensive, though of course I'm happy to talk about this more later. So the title is Equivariant Uniform Confibration Model of Cubical Homotopy Type Theory. So the goal of this project was to build a constructive, meaning using constructive logic, cubical sets-based model of homotopy type theory. And so this should be also a Quillen model structure. So we have this idea that homotopy type theory can be interpreted in a model category, though it's got to be a model category with some like additional bells and whistles. So you want something that's called the Frobenius property that says that fibrations can be pushed forward along fibrations to other fibrations. You need something about universes. So this is sort of a model structure plus. And the hope is that the resulting model category will be at least classically, meaning proven in sort of standard classical logic, equivalent to spaces. So there are a number, there are a bajillion model categories that are Quillen equivalent to Quillen's original model structure on simplicial sets, but that don't give a constructive cubical sets-based model of homotopy type theory. Or there are, as we'll see on the next slide, sort of constructive cubical sets-based models of homotopy type theory that aren't Quillen equivalent to spaces. So when we were working on this project, we weren't aware of a model structure that satisfied these conditions. So that was the goal. If that's to be achieved, there's sort of some additional things that maybe aren't quite as essential, but would be nice bonuses. You'd like the comparison Quillen equivalence to be via nice functor, sort of abstractly, two model categories are Quillen equivalent if there's a zigzag of Quillen equivalences between them, but that, in practice, that doesn't give you a nice way to translate back and forth between the model categories. So better would be, of course, if we have a single functor, like a triangulation functor that implemented this Quillen equivalence. And the other bonus might be controversial in this seminar, but given my background, I like to use a cube category that here I've used the phrase permits inductive constructions. But sort of what I mean by that is it's a Reedy category in some sense. So I'll give some indication later on where the readiness comes into play. Okay, so that was the project. And let me give a little bit of the history. So again, there are a whole bunch of model categories that are Quillen equivalent to spaces, but they aren't maybe made with constructive logic, or they don't have these extra sort of bells and whistles that are important for homotopy type theory. By contrast, there are several sort of cubical set space models of homotopy type theory, and I wanted to sort of review the history, though this list is not given in historical order. So there's what's called the BCH model due to Besem, Kokon, and Huber. And the cubes they use are what are sometimes called the symmetric cubes. So this is the category of cubes that has the faces and degeneracies, which all cube categories have. And then in addition, the symmetries, which permute the dimensions. So, so there's a Z mod 2 symmetry of the 2 cube. There's an S3 symmetry, or I guess I'm going to say sigma 3 later on. There's a sigma 3 symmetry of the 3 cube permuting the 3 dimensions, a sigma 4 symmetry of the 4 cube permuting the 4 dimensions. That's what I mean by the symmetries. So that was the first of these sort of constructive models of homotopy type theory, but it is not equivalent to spaces. So the proof of this is, it's a pretty subtle argument due to Ulrich Buchholz. The way they show that it's not equivalent to spaces is essentially they find a particular object in that cube category. So this is the quotient of the 2 cube by the non-trivial symmetry. And that should be contractible, but is not, so it should be equivalent to the point, but it's not equivalent to the point. So this is a cofibrant object in the model. So it's, I mean, it should be contractible, but it's not. The proof of that goes through a comparison with the test model structure on this cube category. So there's sort of a commutative up to homotopy diagram that shows that that it suffices to prove that this object is not contractible in the test model structure. And so in the test model structure, there's this characterization of the, so what it means for this cubical set to be contractible would mean that the category of elements would be sort of weakly contractible, meaning it's the nerve of the category of elements is a weak homotopy equivalent to the point. And you can use Quillen's theorem A to simplify the computation of the homotopy type of that by sort of looking at a sub-poset contained within the nerve of the category of elements of this cubical set Q. And kind of the key idea here is that there's this symmetry without a map in the cube category, a diagonal map in the cube category that identifies its fixed point. So the symmetry preserves the diagonal, but because the diagonal isn't present at a morphism, that's kind of what's contributing to the non-contractibility of that homotopy type. Okay, but anyway, that's one of the models. These are given in order of complexity of the cube category. So another cube category is what we might call the Cartesian Hues. So these contain the faces, the degeneracies, and the symmetries as before. Symmetry, remember, means you're permuting dimensions. But in addition, they have the diagonals. And what the symmetries and the diagonals mean is the sort of monoidal product that takes an n cube and an m cube and gives you an n plus m cube is now a Cartesian product, which is why these are called the Cartesian cubes. So these were explored by Aude and then separately by Angiuli, Bruneri, Kokon, Favonia, Harper, Licata. So these are sometimes called the ABCFHL cubes. The argument that I sort of sketched due to Ulrich Buchholz that shows that these are not equivalent to spaces for the same reason, or for the same, on account of the same cube. So again, the quotient of the 2 cube by the non-trivial symmetry will not be contractible. That argument doesn't work anymore because the diagonal is there, and but there's a sort of more subtle argument due to Christian Settler that sort of considers maps out of this and gives some sort of non-contractibility of that. That is the reason why this is known not to be equivalent to spaces. And then the final common constructive cubical set space model of homotopy type theory is due to Cohen, Kokon, Huber, and Mortberg. And they actually have 2 different versions of this. Chris has talked about this in the past, though unfortunately I'm using different names than I think he did. So the original paper uses what are sometimes called the Demorgan cubes, because this has something to do with the Demorgan algebra. And so these have everything. So it's the faces, the degeneracies, the symmetries, the diagonals as before. In addition, they have the connections, so both the min and the max connection, and then also a reversal. So a reversal is an automorphism of the one cube that switches 0 and 1, switches the two endpoints. Here, Buchholz's argument can be reprised to show that the one cube, the interval modulo this reversal, is not contractible for kind of the same reason. So you can compare this model structure with the test model structure, and in the test model structure, look at the category of elements and a subposit of that, and you can see that you have this automorphism without having a map in the cube category that picks out its fixed point, so that picks out the midpoint of the interval, and that gives some sort of contradiction. But as Chris noted whenever he mentioned this, there's sort of nothing that, none of the constructions that establish this as a model of homotopy type theory really make use of the reversals. And so there's what Steve Aude likes to call the Demorgan cubes, which are faces, degeneracies, symmetries, diagonals, connections, but no reversals. So this is equivalently the category of cubes that are sort of full on the posets, which are 0 less than 1 to the n. So these are the sort of full embedding of cubes into cat or in poset, these Demorgan cubes. And this is an open problem. So nobody knows anything about this cube category. I think Martina's gonna tell us a bit about it on Wednesday.
Emily, does have upper and lower connections?
Yes, yeah, connections for me mean both max and min.
Oh, okay. Has anybody looked at it with just one of those?
Let me defer to somebody else. Chris, do you know?
I don't know of any work on that topic. So doing something like Demorgan, but with only one connection, I mean, when you have reversals, you kind of want to have the other connection as well.
I know, but now we gave up the reversals, so it raises the question. Yeah. Okay.
Yeah, I don't know of anything.
Okay. Thanks.
Right. So really kind of the world expert on this question of are things equivalent to spaces is Christian Sedler, who I guess I mentioned here and has been thinking about this for a long time. And sort of depending on what day you catch him, he goes back and forth and saying whether he thinks expects this to be yes or expects it to be no. So it's definitely an open problem. And there are a lot of people who would love to see this resolved one way or the other. I think it would be interesting either way. So that's a challenge. Martina and I worked at this for a while and thought we had it, and then it all kind of fell apart. But okay. So that's sort of the history of the problem. And now I'm going to tell you the idea for our project and then what we do. So you can see, I guess, we have, in the cases where we know that some particular cubical sets model of homotopy type theory is not equivalent to spaces, the issue has to do with some quotient of some of the cubes by some sort of symmetry, the swap in this case and the reversal in that case. So it's possible to show by some complicated argument that those objects are not contractible. So to rectify this, we're going to make this Q, which will be a cofibrant object in all those models and in our model as well. We're going to make it contractible by making the inclusion of the point into a trivial cofibration. So that will definitely make it weakly contractible. So how do we make this map a trivial cofibration? Well, we're going to redefine the notion of fibration. We're going to make the fibrations more restrictive, so it's harder to be a fibration. And we're going to change the definition of the fibrations so that they lift against these maps, and that's what makes it a trivial cofibration. It's something with the left lifting property with respect to the fibrations. So specifically, we're going to add an equivariance condition to the definition of the fibrations. And I want to illustrate sort of how that's going to work. And then, one of the main themes of the talk is to come back and give a precise accounting of this equivariance. That's the one sort of technical detail that I'll try and go over enough times that it makes sense. So let's just consider a particular, we need to deal with this counterexample for all cubes. So the equivariance condition will refer to all cube dimensions, but let's just think about the case of the cube, all cube quotients. So we have Q, which is just the quotient of the 2 cube by the swap. So that's here. It has a vertex, I'm going to call it 0, 0, sort of one of the vertices that's fixed by the swap map. And we want the definition of fibration, so x to y to be a fibration, so we want to give a sort of new definition, a strengthened definition of fibration that will mean that there's a solution to this lifting problem, because that's what's going to make this a trivial cofibration. So we're going to make this map a trivial cofibration, the inclusion of the point into Q, by adding some lifting property to the fibrations so that we can solve a square like this. Okay, so here's how we're going to construct, and this all needs to be constructive. So it's not just we're proving the existence of a solution, we're going to construct a lift in this square. So how do we get a lift in this square? Well, this Q is constructed as a quotient of the 2 cube. It's the 2 cube modulo something or other. In fact, it's a coequalizer. So here's the coequalizer diagram. So it's the map. It comes with a universal map from the 2 cube that coequalizes the identity map in the swap. That's sort of a way to say what the construction is. So so the idea is going to be, we're going to construct the lift here, which I'm calling JXY, by constructing a lift in this larger rectangle instead. Okay, but that doesn't quite work the way I've explained it so far. I mean, if this were a push-out square or something like that, sure, we know that if you construct a lift in the larger rectangle, then you get a lift in the right-hand square. But this isn't a push-out square, so that it's not going to be enough to just solve this lifting problem. So merely having this dashed yellow lift is not enough to give us the dotted orange lift. But the point is, we're going to require that the dashed yellow lift satisfies an equivariance condition. And so what that equivariance condition says is, so firstly, my fibration will be able to lift against maps, which are an inclusion of a point into the interval or into the 2 cube. That's a normal, the open box filling that certainly gives you that much. But then those lifts are required to be specified in a way that means they're compatible with certain squares between the generating cofibrations. So if you look now at this outer rectangle, I guess I didn't label that map, but this is the same 0, 0. This is the same inclusion of the point into the interval. So certainly if I have a lift here, I have a lift here. And then the requirement is that this lift restricted along that swap map is the same as this lift. Or another way to say it is that the dashed lift forms a cone. Well, right, I guess in this particular case, it's going to say that this sort of dashed lift forms a cone under that coequalizer diagram. So I've written out the equation here. What the equivariance condition is going to look like is it's this equation in yellow that says that if I take this thing and I restrict along the swap map, then I get the solution to this outer lifting problem. So I should say these parameters in here are indicating what the source and the target are. So this, in a commutative square in a lifting problem, we have the source map and the target map. And this X is the name of the source map. This Y pi is the name of the target map. So that's why this lift was called J of X, Y pi. When I precompose with swap, now I'm supposed to get a map from the here to here. And that's meant to agree with the specified solution to the lifting problem whose domain is X and whose codomain is this composite swap pi Y. But the point is, because this pi is a coequalizer of the swap and the identity, pi precomposed with swap is just pi, which is saying that this J, X, Y pi precomposed with swap is just J, X, Y pi. So in other words, this is a cone under the coequalizer diagram and thus induces a map through the quotient. So that's kind of the idea, is that what fibration is going to mean is we lift against certain maps. That's kind of what fibration meant already, but we're going to impose an additional equivariance condition that means that those maps can form cones under certain sorts of quotienting diagrams. And that's what's going to make these maps into these cube quotients into trivial cofibrations as well. So that's a preview of an idea that I'll repeat again. That's kind of the new idea in this model, this equivariance condition. And then our theorem is going to be that we achieve the goal. So that we will introduce something, a notion of fibration called equivariant uniform confibrations on the category Cartesian cubical sets. So these are one of the Cartesian cubes are the ones with the faces, degeneracies, symmetries, diagonals. And they're going to satisfy the above desiderata. So this will be equivalent to spaces. the Quillen equivalence will be by a nice functor. It's triangulation functor. And the cube category is one of these reedy sort of cube categories. So the plan for the talk, I'm going to first tell you about the cube category. Tim's actually kind of covered this already, but I think it doesn't hurt to see it again. So I'll explain why the category of Cartesian cubes is easy, or an Eilenberg-Zilber category, which is one of these sorts of reedy categories, generalized reedy categories. Then I'm going to give you the definition of this equivariant uniform confibrations and explain again how this kind of equivariant stuff works. And then at the end, I'm going to sketch the proof of the Quillen equivalence to spaces. And that part of the argument is actually just due to Christian Settler, but I'll give you his proof. But any questions about any of that before we carry on? Okay. All right, so let me tell you about the cubes we're going to use. So there's a very quick definition of the cube category, the Cartesian cube category. So it's equivalent to the opposite of the category of finite bipointed sets. So these are going to be a finite set that has a base point 0 and a base point 1, and we require that 0 and 1 are two distinct base points, and then they could have some other finite number of elements. So here on the left, I've displayed the notation that we'll use for the objects in the cube category. So as you're familiar with, we have a cube in each dimension. We have the 0 cube, I'll also write as a star for the point. The 1 cube, I'm going to call I. The 2 cube, I'll call I to the 2. But in this Cartesian category, this is really I times I, the Cartesian product, 3 cube, etc. We have all the finite dimensions. And if you want to think about them, it's productive to think about them again as these finite bipointed sets. So the point corresponds to the pointed set that has just the two base points 0 and 1. The interval corresponds to the finite bipointed set that has 0 and 1, and then one element that's neither 0 nor 1. And if we stop and think about the maps between these two objects, maps of finite bipointed sets have to preserve both base points. So there's two maps from this set to this set, because you can send either x to 0 or x to 1. And there's one map from this set to this set, because you have to send 0 to 0 and 1 to 1. And those will correspond exactly to the faces and degeneracies that you're familiar with. And then similarly, the 2 cube you can think of as having this sort of finite bipointed set. The 3 cube is this finite bipointed set. There's this nice intuition that the computer scientists have, which is that these elements are like dimension variables, or so x, that 1 cube should have one free dimension variable. Its 2 cube should have two, free dimension variables, and so on. The 3 cube has 3 dimension variables. Okay, so I left this as an exercise because I think this is one of those things that if you do for yourself, you learn a lot more. So as I mentioned, there are 4 types of maps, but then there are also, of course, the composites of these maps, which won't necessarily be exactly one of these 4 types. These are the sort of faces, the degeneracies, the symmetries, and the diagonals. I'm indicating sort of what dimension these things start in here. So the smallest diagonal goes from the 1 cube to the 2 cube. The symmetries start in dimension 2, or the non-identity symmetries anyway, and so on. And it's a good exercise. I think it's illuminating. It gives good intuition for these maps if you work out what they correspond to as maps of finite bipointed sets. So that's a bit of fun for you. Okay. So I guess this is probably pretty familiar. I'm not introducing notation for any of these because we won't need them. But maybe I guess the one thing that'll be important later is, how many symmetries are there? Maybe I'll ask this as a question. How many symmetries are there of the n cube? Chris can't answer, somebody else. So I'm asking, what is the automorphism group of the n cube? That's sort of the language we'll use it as an object in this cube category.
We're going to
seem like it.
Right?
Sorry, 2 of you answered at once, and so I didn't hear either, of course.
I think we both said sigma n.
We definitely need this going on, so I just can't proceed without this information. What is the automorphism of the n cube?
Seems like it's the symmetry group on n elements.
It is the symmetry group on n elements. Great, thanks. Yeah, and that's, I mean, these calculations are sort of easier in the finite by pointed set side, but great, good. Yeah, so we'll use that. I'll write sigma n for it later on. Okay, so what I wanted to tell you about this category, you know, everybody has their favorite cubes. And so the reason these are my favorite cubes is because they're an Eilenberg-Zilber category. Another example of an Eilenberg-Zilber category is delta, the simplex category. And if you're one of those people who feels pretty happy working with simplicial sets and feels like, you know, I don't know, you know how to construct various things and give various arguments, probably the reason you know how to do all that is because it's an Eilenberg-Zilber category. So you should be happy to know that the Cartesian cube category is one of them as well. So let me just tell you what that means. So this is a, so our cube category, which I guess I'm just gonna write like this until toward the very end. So our cube category, the objects have a natural dimension. So the 0 cube has dimension 0, the 1 cube has dimension 1, etc. And that then it has this structure of an Eilenberg-Zilber category. And what that is it's a bunch of additional properties now. So what are these properties? So the first is that if we look inside this cube category at the isomorphisms, then if you have an isomorphism, the dimension of its domain and the dimension of its codomain are the same. That's the first part of the statement. For any isomorphism, the dimension of the domain is equal to the dimension of the codomain. Then there's also the statement, if I have a monomorphism that's not an isomorphism, so a non-invertible monomorphism, then the dimension of its domain is less than the dimension of its codomain. And then if I have a split epimorphism, that's again non-invertible, so not an isomorphism, then the dimension of the domain is greater than the dimension of the codomain. So that's, that seems pretty innocuous, but that's one of the requirements, essentially, that this dimension function agrees well with the monos and the epis in the category. Okay, I should say what are these maps? So back to the previous slide, the epimorphisms are going to be things that are composites of degeneracies, or the non-invertible epimorphisms are things that are composites of degeneracies, maybe with some symmetry or something like that. These are all split. So a degeneracy is like collapsing one of the dimensions, and you can split it by including a face at sort of 0 or at 1, kind of in orthogonally to the dimension that you collapsed. So that's what the split epimorphism business is about. Okay, so property 2, easy property 2, is that we can factor any map. So the objects in the cube category, remember, we're writing like this. This is the n cube, this is the m cube. So you can factor any map from an n cube to an m cube through a split epimorphism followed by a monomorphism. And moreover, that factorization is unique up to isomorphism here. So in sigma k, which is the automorphism group of the k cube. So there's an essentially unique way to factor. The only difference is you might permute sort of the coordinates in the essential image. I guess that's a way to think about it. But otherwise, we have this unique factorization into the left class and the right class. And then the final property is the least familiar, and it says that the split epimorphisms have absolute pushouts. So let me explain what that means. So firstly, in this cube category, I need to have, if I put one of these split epimorphisms here and one of these split epimorphisms here, so these are the degeneracy maps, and I form the pushout. So the first part of this absolute pushout statement is that that pushout exists. So you know, the cube category is pretty small. You wouldn't necessarily expect it to have a whole lot of stuff going on, but it needs to have this absolute pushout, or this pushout. And then the absolute business means that it's got to be preserved by every functor. So it turns out by some Uneta magic that in a small category, something or other is a square is an absolute pushout if and only if it's a pushout that's preserved by the Uneta embedding. So that's going to be one way to verify this absolute pushout property. But actually, it's sort of as easy to see that it's an absolute pushout in general. But the notation here I've used is using this Uneta embedding. Okay, so firstly, I'm going to argue that I have this pushout, and then I'm going to argue that it's an absolute pushout. So to see that I have this push out, if we're working just in the cube category, so this is some, ignore the funny notation for now. If this is some cube, and this is some cube, and this is some cube, I want to form the push out. Remember, my cube category is equivalent to the opposite of finite bipointed sets. And it's, again, that's just a little more concrete. It's easy to see that you have pullbacks of monomorphisms in that category. These split epimorphisms correspond to monomorphisms of finite bipointed sets. Or you can just sort of guess what the answer is and what it should be. So what I've written here is, rather than write I to the n as the n cube, I've partitioned its variables. So there's some number of dimension variables in the x, some number of dimension variables in the y, and some number of dimension variables in the z, and the number of total variables is n, say, if this is an n cube. And then, so this epimorphism is meant to be the one that projects away from all of the dimension variables in z. This epimorphism is the one that projects away from all the dimension variables in x. And then you can see the push out in that case is the cube, which is indexed by those dimension variables that are common to here and here. It's some sort of intersection of finite pointed sets. So that's the push out. Okay, so that's meant to be an argument that I do have push outs in the cube category. To say that they're absolute push outs, I need to say that when I pass to cubical sets, so here's the category of cubical sets, this hat over some category means pre-sheaves on it. So in the category of cubical sets, I need to argue that this is still a push out. And if you tried to imagine how you would show such a thing, like the one example of an absolute colimit or the first example that I was familiar with anyway, are these like split coequalizer that come up in the statement of the monadicity theorem. And basically what a split coequalizer is it's like a coequalizer diagram. I guess really, so a coequalizer is like a parallel pair, and then it's the fork or the cofork. So it's a coequalizer diagram. And then you throw in a bunch of other maps and a bunch of equations involving those maps that somehow equationally witness the universal property. And then like, once you sort of understand that these two maps and some conditions imply necessarily that that bit is a coequalizer diagram, now it's super clear that it's going to be preserved by any functor because, functors preserve composition and stuff. So it's the same sort of idea here. So the reason this is an absolute push out is, well, firstly, these split epimorphisms all have sections, and you can choose the sections in such a way that they're compatible with the other maps. So so you can choose a section here and a section here so that the diagram formed by these upwards pointing dashed yellow arrows and the horizontal white arrows commutes. And you could do it the other way, but that turns out to be enough for this to show that this is a push out. So that's another just fun one category theory exercise you can do if you like. Or when I was thinking about this, I wrote something on the NLab, and then when Mike was thinking about this, he wrote something more on the NLab. So there's this sort of, you can read through the history of absolute push out on the NLab, and it kind of discusses this example. So.
And of course, when Zach, Z, and I were writing our paper, we didn't know of any of that. And we also have this little fact included somewhere in the paper.
Great. Yeah, and it sounds like Tim discovered this as well. So everybody agrees it's an absolute push out. Great. Good. Yeah. Okay, so that's all I was going to say about the cube category. This is the end of part one. But I'll pause again for any questions. So I guess an open question at this point should be like, why am I so excited about this? And I'll say a little tiny bit about that later on. But,
I just went onto the NLab page for absolute pushout, and I'm kind of surprised to find that the original reference, which is a paper of Bob Perret, isn't there.
Ah, well, that's because I didn't know it, and I'm the one who created that page. So
okay,
that's my fault. Send me an
email. No, that's fine.
Send me an email and I'll fix that.
Oh yeah,
maybe
sure.
After the talk.
I thought I remembered a Perret paper on absolute coequalizers. I didn't realize that he also wrote about absolute pushouts.
Yeah, he gives the general characterization of absolute pushouts.
Okay, well, neither of us knew that, so sorry. But yeah, thanks for the reference. No. Okay, good. So what's next? Right, so now I want to start to tell you about equivariance. So the end of this section is going to be the definition of the fibrations in our model. So we call them equivariant uniform confibrations. But I want to warm up a bit by kind of revisiting the idea in the introduction about how an equivariance condition might be expressed as part of a lifting property. So I want to start with a simple category. So this is the category of, I'm going to call them right sigma n sets. So sigma n is the symmetry group. This is a pre-sheaf category. I guess I could have just said sigma n hat, but it's the category of contravariant functors from sigma n into sets, right sigma n sets. So you can think of this x and this y now as sets with a sigma n action on the right, and then a map should be an equivariant map, so a map that respects the action by elements of the symmetric group. Okay, so there are two, I want to sort of draw your attention to two different weak factorization systems on this category. In fact, they're the injective and projective ones with respect to the monomorphism, epimorphism, weak factorization system on set, if you want to think about it that way, but we can just kind of describe them elementarily. And actually, I'm not going to focus so much on the whole weak factorization system, just on the right class. So the first claim is I can characterize the epimorphisms in this category. So a map F, so the equivariant map of right sigma n sets is an epimorphism if and only if it lifts against a single map here. So this is the empty set, which has its trivial action. And this is sigma n as a right sigma n set. So this is the sort of right action by right multiplication on itself. So the first claim is that F is an epimorphism if and only if it has this lifting property. And I want to think about why that's true. So what does it mean to say that there's a lifting property? So I can consider the set. So this is a Hom set in the category we're working in, so in right sigma n sets. So I can consider the set of maps from here to here. These are like the set of diagonal maps. And then there's a function from that set. So this is to the set of commutative squares, which decomposes as this pullback here. So to define a commutative square, you have to define the top map. That's an element of this set. And then the bottom map, that's an element of this set. And then you need to check that they commute. So that's some condition that ends up being vacuous in this case, I guess, because that's initial, but whatever. So some pullback defines the set of commutative squares. And then there's a map from here to here that's given by this lifting problem. So because of this specific map F and this map, which I didn't name, there's a function from here to here. And to say that any white square has or maybe to specify a solution, a diagonal lift to any white squares to specify a section to that map. So that's giving sort of a set theoretical way to redescribe these lifting properties. But this is the free right sigma n set on a single element. So the set of maps in this category from here to here is just the underlying set of X, kind of forgetting about the action now. And similarly, those things are singleton sets, and then this is the underlying set of Y. So to say that I have this lifting property is to say that this map has a section, but this map is just the underlying map F, forgetting about the equivariance. So that's the sense in which F is an epimorphism if and only if it has that lifting property. Okay, so the example that I'm more interested in is the one over here. So now I'm going to characterize what it means for F to be a sigma n split epimorphism. And so what that means is this is well, it's a split epimorphism in the category of right sigma n sets. So you witness that something is an epimorphism by constructing a section, but here the difference from over here is that section needs to be a sigma n equivariant map. So I'm not just choosing an element of the fiber, I'm choosing an element in a way that would respect the sigma n action. So the claim is that I can express this also as a lifting property, but it's a lifting property that doesn't just say I need to specify solutions to lifts in individual commutative squares. I'm also going to consider kind of a category of generating left maps is one way to talk about all of this. So I need to solve this lifting problem, but then I'm going to have a requirement which says that if I sort of paste on the left with a certain rectangle between these kind of generating left maps, or square. So this is the square that uses one of the symmetries acting on the left. So that's a sigma right. This is a map of right sigma n sets, left multiplication by a sigma is a right sigma n set. In fact, all well, there's some Uneta thing I can say. So anyway, the condition is now that F needs to have solutions to lifting problems, but moreover, when I specify a solution to this lifting problem, and also specify a solution to the lifting problem posed by the composite rectangle, this specified solution restricts along that map to that specified solution. So that's a condition you could ask. And F has a lifting property like that, sort of if and only if it's a sigma and split epimorphism. Well, what's the proof? So we can go, we can express the same style of reasoning. Again, to say that I had a solution to a single lifting problem, just this square on the right, it would say that this map of sets has a section. But to say that those those lifts are compatible with the maps here is to think of this not just as a set anymore, but as a right sigma n set. So these left multiplication maps by precomposition give this Hom set a right sigma n action. So if I think of this as being an epimorphism in the category of right sigma n sets, now having this lifting property that's equivariant is amount to having a section, but in this category. And again, this is the free right sigma n set on a point. And so this thing is actually naturally isomorphic to just X itself. I guess that's the innate lemma. So this is just X and that is just Y. So I'm asking for a section in that category. All right, so I'm somebody who's well acquainted with algebraic weak factorization systems. And if you're used to thinking about that sort of thing, this is a pretty familiar idea, but if you haven't seen it before, this might be new. And yeah, so this is, I guess the high level summary is that, lifting properties can give some sort of structure on the right maps. And if you add an equivariance condition, then that's going to impose a refined structure. So certainly sigma and split epimorphisms are epimorphisms, but this is something sort of more special. And we're going to follow the same pattern, basically. Okay, so the goal again is to tell you what the equivariant uniform confibrations are between Cartesian cubical sets. Before we do that, I'm going to tell you what the trivial fibrations are, sort of as a way of warming up. And actually, if you're well acquainted with Reedy machinery, I can give you a one-sentence definition. So we saw on the previous slide this weak factorization system for where the right maps are these sigma n split epimorphisms. And if we do the induced Reedy weak factorization system with respect to this generalized Reedy category, then that's the one that I'm about to describe for you. But I suspect relatively few of us are familiar with any of those terms, so let me just tell you what it is. I'm going to unpack this. I should say there's some subtleties from the algebraic weak factorization system perspective. You can ask me about that at the end. I don't want to get into that now. But the underlying weak factorization system is just the Reedy one with respect to the thing I just told you about. But okay, so here's the definition. So they're called uniform trivial fibrations. I should say the cofibrations are monomorphisms. So that would be one way to say what they are. Anyway, so a map of cubical sets, Cartesian cubical sets, so this is a map in the pre-sheaves on the cube category, is called a uniform trivial fibration if and only if it satisfies the following lifting property. So firstly, if I'm given any cube, so n could be any dimension, and then any subobject of the cube, so this could be like a boundary or a horn or a diagonal or a point or empty or whatever, any subobject of the cube, then I get a commutative square and I need a specified lift in that square. And then the uniformity, so this says uniform trivial fibration, says that if I have any pullback square between these subobjects of cubes, so the data of that is my original subobject of a cube and then a map of cubes here, the pullback is then determined by that data. Then I have a uniformity condition, which says that this specified lift restricted along the map of cubes alpha agrees with that specified lift. Okay, so that's just the definition of the trivial fibrations. If you were expecting a different definition of the trivial fibrations, there are like 6 equivalent ways to say this, and the one you were expecting might well be this one. But this one is sort of most closely parallels the fibrations, which is why I'm emphasizing it here. Let me give some indication of what this gives you. So an instance of a pullback square between subobjects of cubes is I can think about the boundary inclusion. So here, this is meant to be the subobject. This is like the Reedy boundary. So this is the subobject including all of the faces of lower dimensions. So it includes like the diagonal in the cube, for instance. And then if I had an automorphism, so a symmetry, an element of sigma n, that gives me a map between these cubes. And when I pull back, I'm going to get the same boundary, but I have a permutation here as well. So this is an instance of a pullback square. And so I have some uniformity condition. So that means that a trivial fibration comes equipped with solution to a lifting problem like this, that when I restrict along this symmetry is equal to whatever this is going to be. And let's now unpack what that is in the kind of the way we did on the previous slide. So to solve a lifting problem like displayed by this right-hand square is to say that if for any map in the category of cubical sets from in into x, I have a map from that down to the set of commutative squares, which is the set of boundary maps from the boundary of that into x paired with n cubes and y, such that something or other commutes. I need some sort of section, but again, because of this equivariance condition, this is in this category of right sigma n sets as opposed to just in the category of sets. So by the innate lemma, this set here is just x to the n. This set here is just y to the n. And the set of maps from a boundary of an n cube into x is something in Riehl category theory that's called the matching object. So this mnx is the standard notation from Riehl category theory. This mny is the standard notation from Riehl category theory. These are sort of boundaries of cubes in boundaries of n cubes without the n cube itself. These sets get a right sigma n action just by precomposing with one of these symmetries. And so a feature of the trivial fibrations is that I'm going to have a sigma n equivariant section to this map. So if you're familiar with using, well, I guess if you're familiar with the notion of, or how you use sort of Riehl stuff to inductively define solutions to lifting problems or inductively define maps, this is the sort of thing that would be kind of exciting. So I don't know, if you're trying to lift something that's defined from y up to x, inductively at step n, you've done it for all the previous dimensions. That's kind of the bit that's seen by this mnx and mny. And so you need to kind of lift along a thing like this, but it's a little more complicated in this generalized setting because we have these symmetries. And so having an equivariant split map is going to solve that problem for you, basically. So that's sort of what the trivial fibrations are about. Okay. Right. So so now I want to. So the rest of the section is about the fibrations, other than the trivial fibrations, and so I'm going to describe for you firstly what the generating trivial cofibrations look like. So these are the maps, so that the fibrations will be the things that are lift against things like this. So here I want to describe the basic recipe. This is kind of a warm up what's going on the left here. This is the basic recipe for building a trivial fibration. So for these cubical sets models, you're used to the trivial cofibrations as being things like open boxes. And essentially what I want to explain is where open boxes come from. So what's an open box? So firstly, you should start with a subobject of the n cube. Maybe for geometric intuition, this should be like the geometric boundary. So it's kind of the bits that you would paint if you painted the n cube. And then we're going to start with an inclusion of either of the endpoints of the interval. So this could be mapping in at either 0 or 1. We'll have both possibilities. And then there's this thing called the push-out product construction. What push-out product is it's a functor that takes a map of cubical sets and another map of cubical sets and returns a map of cubical sets. And if you apply that construction to this thing and this thing, here's what you get. So in the codomain, you're just going to take the product of these two objects. So this will be the n+1 cube. And then in the domain, what I'm going to do is I'm going to form a push out of various things. What it reduces to in this case is I'm gluing c times I to the n cube along c. Right, so this in the case again when this is the geometric boundary, this is giving exactly an open box. So open boxes are formed. The summary is that open boxes are formed by taking push-out products with the inclusion of one of the endpoints of the interval. And if you generalize this notion of open box to allow kind of lower dimensional open boxes, that's where we have this general subobject here, not just any particular one. So that's kind of the idea of an open box. And what we're going to use is we're going to use It's basically the same idea, except we're allowing these sub-objects to occur in sort of the context of an arbitrary cube. So if we're thinking about cubical sets as being a model of homotopy type theory, the types correspond to the fibrant objects, and a type in the context of a cube, say, or in the context of a cube variable will be a fibration over that cube. So so that's kind of what I mean. So when I say something is something in context of a cube, that means I'm not just thinking of it as a map in cubical sets anymore, but a map in the category of cubical sets sliced over the K cube. The way we're going to produce this, it's essentially the same push-out product construction, where one of the inputs will be an arbitrary subobject of an n cube, but I'm going to think of that n cube now as living in the context of a K cube. So I'm going to include an arbitrary map of cubical sets here, and think of this as being an object in this category of cubes sliced over the K cube. So that's one of the inputs. And an advantage of that is it gives us access to something that's called like the generic element of the interval. So this would be easiest to explain in the case k equals 1. So that might be a good thing to think about. So if we, in the case k equals 1, so this is the interval, this is I times I, this is I. But in the category of cubical sets over I, this I times I just looks like the single interval. Sort of one of the dimensions is sort of pinned down by the projection and the other one is free. This is like the point. This is the terminal object in the category of cubical sets over I. And before I only had 2 points in the diagonal. I had sort of the 0 and I have 2 constants in the interval. I have 0 and 1. But when I pass to this slice, I get a third one, which is the diagonal. And that's what I mean by the generic element. So if you're expressing this stuff in like the internal language for a pre-sheaf topos, like if you're using sort of a type theory way to give a name to this map, this becomes clearer and it's a little more mysterious for sort of category theorists like me to think about. But so the idea in the sort of K, this is an idea I learned from Thierry Coquin, though I think maybe it goes back to Bill Levere. Alex can correct me, I'm sure. But the idea is, if I think about the K equals 1 case of this, this is giving me something like a generic element of the diagonal. So it's like having constants that aren't 0 and 1, or something that's going to move you across the interval. But we're going to do this in all dimensions, which is why there's a K. And then we just do the push-out product construction as before, but really it's like a push-out product where the product is itself a push-out, which is why we've got this sort of sub thing here. And I'm just going to give you the computation. So this is some functor that takes a map of cubical sets over the K cube and a map of cubical sets over the K cube, does some construction, push-out product construction, gets a map of cubical sets over the K cube, and then we're going to forget that we were over the K cube at all. And so this is what you get as the result. So the codomain is just going to be the product of the codomains. So this and this, but I guess really it's a pullback over I to the K, which is why we just get an IN times IK. And then this is the thing that I'm going to call like an open box. And you can see it's kind of like before, except for there's an I to the K now where there was an I before. I mean, so it's basically the same thing, but there's an I to the K where there was an I before. Okay. So this is I'm not going to write these massive diagrams ever again. So when you see something like this, this should be an open box. So it's the analog of an open box. It's some subobject of the n plus K cube, and the inputs are a subobject of the n cube together with a map from n to K. So that's what these subscripts are indicating, or sort of what determines which subobject this is, basically. That's going to be a trivial cofibration. And so as with the definition of the trivial fibrations, the uniform trivial fibrations, there are going to be some squares between these trivial cofibrations that will impose uniformity conditions, though I'm going to call them sort of a uniformity and equivariance condition, because really these squares are built as push-out products of 2 different squares, and they each give a different half of the condition. So I should say you should think about so I'm going to build a square so that the left side of the square is one of these open box inclusions, and the right side of the square is another one of these open box inclusions, and then there's going to be some maps between them. And remember, these open box inclusions are push-out products of something which is like a generating cofibration with something like a generating trivial cofibration. So this is in the generating cofibration variable. I have just, this is exactly the same uniformity square as before. I have some subobject of the n cube, an arbitrary map of cubical sets, and then the pullback. So the input on this side is a pullback square where the codomains are cubes. And then the input on the right, so the right, this is the thing that's the, sorry, we've got a, there's 2 rooms in this apartment, and the door doesn't always stay closed, but let's give it an attempt. So, okay, so the square on the right, this is something that replaces the inclusion of a point into the interval. This is kind of giving me access to a generic element of the K cube. And then this is a twisted version. So this is just the diagonal map. So it's identity paired with identity. This is a twisted version of the same thing where I stuck in one of the symmetries. And then there's a commutative square between them that puts a symmetry on the leg where there was a symmetry. And when I push out product those things together, I'm going to get a square between 2 of these generating open box inclusions. And this is what's giving us the definition of a uniform equivariant fibration. So this is the last bit of part 2. Let me sort of talk you through it. So a map of Cartesian cubical sets is a uniform equivariant fibration. In other words, a fibration in our model structure, if and only if it can be equipped with the following lifting data. So we need to solve, need to have specified solutions to a bunch of lifting problems. And those lifting problems are indexed by, firstly, a subobject of an n cube, and then a map from the n cube to a k cube. So as explained in the slide 2 previous, given this data, I get one of these open box inclusions. You can just remember, pretend this is a usual open box inclusion, but it's sort of a more general notion of open box inclusion. Now I can consider an arbitrary commutative square. The reason I've used 2 different variables to label this top map is this, you could remember, was glued together from 2 different pieces. And so the X is like the map from one of the pieces and the W is the map from the other piece. So I need a specified solution here. And of course, what the name of this map is going to depend on what X was and what W was and what Y was and what the C was and what that, that's meant to be a C, that now looks like it's zeta. Okay, but then these specified lifts need to respect these uniformity and equivariant squares that we just constructed. So if I have a pullback square and also a symmetry and I push out product those together, I get a square that looks like this between 2 different open box inclusions. And the requirement is that this specified lift J restricts along this map alpha times sigma. Sigma is a symmetry, alpha is an arbitrary cube map to this specified lift. And you can write this all out equationally. What it says is that this J, depending on this X, W, and Y, restricted along that is this other J, but now it's for the composite rectangle. So the top is X alpha and then W A times sigma, and the bottom is Y alpha times sigma. So that's kind of all what's written out here. And that's the end of part 2. So maybe this would be a good place to stop for questions.
So this is Ezra. I just wanted to check this. So uniformity is something that you could apply in a variety of situations, and you're choosing to apply it in this situation. It's not, I didn't quite follow, but the uniformity wasn't incorporated in all your trickery with fibered.
That's right. So this uniformity is a standard, what do I want to say? So we're familiar with, so if you're thinking non-algebraically, you're familiar with the definition of trivial fibrations as something that lifts against monomorphisms. What I wasn't familiar with is that if you're implementing that definition, if you're defining a weak factorization system like that in any like pre-sheaf topos, then it turns out there's always a classifying monomorphism. and using that classifying, sorry, this isn't the subobject classifier. It's something like that. And I think I'm messing up the terminology because it's, like I said, I'm kind of rusty on all of this. But there's a universal monomorphism with given codomain for any codomain. And what that means is that classically, if you have a map that lifts against all monomorphisms, it can be made to lift uniformly against all monomorphisms and pullback squares.
Okay.
And that's this, so that idea had been around already, and that's what we mean by uniformity. So you're right, you could use uniformity in a different way, but what uniformity means is you lift against monomorphisms, sort of uniformly in substitution. So I guess from the type theoretic point of view, this is very natural. Pullback squares are substitution, so it's saying.
Right, okay, I see. So it makes pullbacks functorial.
Yeah.
Yeah, which they're not, if you see what I mean. I mean, the usual, I mean, if you just say pullback without any decoration, that's not functorial. But now you're saying, but we can, in type theory, assume.
Well, everything's specified, I guess what I'm trying to say is, so, I mean, what it's saying is if you have a specified pullback square, if you've said this square is a pullback square, you know, and I mean, somebody else might specify a different pullback square by composing with an isomorphism or whatever, but I'm saying this square is a pullback square, then I get a uniformity condition with respect to that particular square. So
but I don't think
it's less unnatural than you think.
But I don't think there's any way that if Chris chose a different pullback square than me, we would never have any clue that that was the case, no matter how many conversations we had, I think. As long as we each made a choice. Okay, anyway.
But the point is this uniformity condition would hold with respect to both of your pullback squares.
Precisely, yes.
So, yeah.
Okay, thanks.
Sure.
Emily?
Yep.
Is any retract of one of these fibrations also one of these fibrations?
Yes. So whenever you define a right class, you know, as lifting against some category, it's automatically retract closed.
Great, thanks.
So, yeah. And right, actually, that's maybe a good. So this is the end of part 2. I've given you the definition of the model structure. What I'm not going to say anything about at all is how we prove this is a model category, though that's a pretty wild part of the story, at least from my point of view. So the type theorists have come up with a completely new way, or the homotopy type theorists have come up with a completely new way of proving that something is a model structure, and then satisfies these extra conditions that makes it the sort of model category that's amenable to interpretation of homotopy type theory. So the first thing that you check is this Frobenius property that says that the fibrations are stable under push forward along fibrations. Then you construct universes and you show some like equivalence extension property and some fibration extension property, and then sort of by magic you get a model structure at some point. So it's like this completely wacky way of getting a model structure. Steve Awaday's given some talks about that recently, sort of geared at a more homotopy, a more classical homotopy theory audience, if you want to hear more about that. But what's
I think that the tool is due to Christian Zattler. I would just add that.
Yes. Okay. Yes.
These are not generic. So it's due to Christian, but I think Steve is doing some.
Great. Yeah. And Christian has a paper whose name is escaping me now, but if you look at his archive listing, you'll figure out which one it is. So there's this like completely crazy way of proving that things are model categories that in certain settings that work quite well in the cubical setting that I was not expecting at all. And what's also really crazy about this is so one of our collaborating team is this Thierry Cocan is a type theorist, and I thought I'm a category theorist. I'm pretty good at showing that diagrams commute, doing diagram chase. This sort of fact that the fibrations are preserved they're pushed forward among fibrations. That's a diagram chase. I just need to show that, define some lift and then check that something or other computes. And it was like completely impossible. But Thierry can write down a one-line proof in type theory using the internal language of this pre-sheaf topos, and it just like completely blew my mind. So I thought about showing that to you, but it would be completely incomprehensible. So I think that's something we should talk about offline. Because I mean, it's just so compact, but it's essentially, I mean, at a high level, what is the idea? So in the internal language, terms correspond. So a term that you define in some context corresponds to a morphism where the domain is like that context, which here you can think of as being like a product of cubes or something. And then the codomain is, you know, a fibrant object or something like that. And so then if you're trying to, I mean, if you're trying to construct something, you're just trying to construct a map that takes as input a certain collection of terms, and then as output gives you another term. And like writing down a function is a lot easier than like arguing from universal properties sometimes. And like that's sort of what you can do with this internal language. But
I thought I'll say I pasted in the chat the papers by Christian
thanks, Chris.
that are relevant. So.
So I only have 2 more slides. I think I might just as well just finish. I realize I'm over an hour, but then we can get out of here sooner. Does that seem amenable, or do people want to take a break? Yeah.
I mean, I think you should just go for it.
Yeah, I'm not going to say that much about part 3, so let me just say it and then we can all get out of here. So the last thing I wanted to tell you about, I didn't give any indication about how we know that this is a model category because it's like wild and confusing. But I did want to give an indication of why it's quill and equivalent to spaces. So this argument is entirely due to Christian Settler. And I thought this might be fun for you all. So what we're trying to show is we have the classical Quillen model structure. So this is where I'm going to use classical logic. So we have this classical Quillen model structure on the category of simplicial sets. So pre-sheaf category on the simplex category. We have the model structure that I just described on, there should be a hat here, on the pre-sheaves of Cartesian cubes. I want to construct a Quillen equivalence between them. And I'm going to bridge between this other category, which are the Dedekind cubes. So that's why I'm annotating these as the Cartesian cubes. The Dedekind cubes are this one that's full on the posets 0 less than 1 to the n. So these are has the max and min connections, but no reversals. So Chris has already talked about this a little bit, but I'll just remind you. So firstly, the Cartesian cubes are a non-full subcategory of the Dedekind cubes. They have exactly the same objects, they just don't have these connections. So that's this map. J is the inclusion from the Cartesian cube category that previously was just written as cubes into the Dedekind cubes. So the simplex category does not map into the Dedekind cubes, unfortunately, but it does map into the idempotent completion of the Dedekind cubes. So that's what this dagger is meant to be. It's the idempotent completion. So if I sort of split, there's certain idempotents of an n cube. You can realize the n simplex is a retract of the n cube in this category. Or not, well, not in this category, but if you add that retract in, then it's there. So this is meant to be the idempotent completion. And all you need to know about idempotent completion is that if you take a category and you take its idempotent completion, their pre-sheaf categories are equivalent. So that's why this isn't going to appear here. So the simplex category is a full subcategory of the idempotent completion of the Dedekind cubes, which means that when I pass the pre-sheaves, so this are pre-sheaves on simplicial sets, pre-sheaves on Dedekind cubes, this is meant to be pre-sheaves on the Cartesian cubes. When I pass the pre-sheaves, now I have these functors, and so I have my restriction functors, that's I upper star and J upper star, and then I have left and right con extension, so that's lower star and lower shriek. So I have this left con extension restriction, right con extension, that arrow's drawn the wrong way. And then I have left con extension, restriction, right con extension again. So I have these 2 adjoint cylinders. They point in opposite directions. So this doesn't compose to a adjoint triple, but anyway. One composite here is the triangulation functor. So if I start with my Cartesian cubes, I do this left con extension. It turns out that's going to preserve representables. So it'll carry the n cube to the n cube. And then if I restrict along this inclusion, it's going to take it to the triangulation of the n cube. You can kind of check that. So I guess this is maybe another exercise, but the composite sort of left adjoint most composite that goes that way is the triangulation functor. So it's visible in this diagram. Okay, so we're going to demonstrate that this model category is equivalent to that model category in 3 steps. So we're using also that Christian Settler has a sort of analogous type theoretic model structure on the Demorgan cubes. So relative to those 3 model categories, the first step is to show that this I upper star J lower shriek are left quillen. So these are the 2 functors that compose to give this triangulation functor. So that will, of course, imply that the composite is triangulation. The second step is to show that J upper star and I lower shriek. So that's the other pair of left adjoints, that both of those are left quillen. And so that's would then imply that whatever the composite of those is, I'm going to call it L. That's a left quillen functor. I should say these proofs are harder than you'd like them to be. So, kind of the easier steps are the middle ones, because the middle ones are left adjoints that are right adjoints also, and that's kind of a good setting to be in, particularly if you're trying to show that you preserve monomorphisms or whatever. This is the one that appears in the literature. It's in Christian Settler's paper on idempotent completion, and the proof is very hard, and we tried to improve it and didn't make any progress. I think it's just these Demorgan cubes are really hard. This is kind of a similar level of complexity. So there's a whole bunch that goes into this, but anyway, whatever needs to see me prove something's left quillen. So what's a corollary then? So the corollary, since all objects are cofibrant in all of these categories, once I have left quillen functors, by Ken Brown's lemma, they preserve weak equivalences between cofibrant objects, meaning they preserve weak equivalences full stop. And that's going to take us to the final step. So just as a review, here I've drawn only the left adjoints from the previous diagram. So I have these 3 functors here and 3 functors here, but I'm dropping the right adjoint. So these are just the things that were left adjoint to something or other. And I've swapped the order of this adjunction so the functors at least compose. So again, the adjunction doesn't compose because this is the left adjoint followed by the right adjoint. So we've argued already that all of these functors individually are left quillen. In particular, that means they preserve weak equivalences. So if I just localize, if I formally invert the weak equivalences and I pass to the homotopy categories, then these functors descend to functors at the level of homotopy category. And then the final step is that I'm going to show that this composite L and this composite T are inverse equivalences at the level of the homotopy category. Not inverse adjoint equivalences, again, because these functors aren't adjoint, but inverse equivalences.
So in the chat, Martina asks, what is the model structure on Demorgan cubical sets, a variant of the version that you constructed in the talk?
So sort of yes and no. Christian Settler has a kind of a paper on, maybe it's the paper that Chris posted about on constructing these model structures on cubical sets kind of very generally. And it turns out that that one so there's no equivariance mentioned in his model structure, but it turns out it implies it. So something about having the extra maps in the Demorgan cubes means that his fibrations, which he just calls uniform fibrations, are sort of automatically equivariant fibrations as well. And that actually goes into proving that something or other is a quillen equivalence, or left. So I guess this J shriek, proving that is left quillen. Part of that means that its right adjoint, J star, needs to preserve fibrations. And what we show to do that is to say that the uniform fibrations in Christian Settler's model structure are automatically equivariant in our sense. So sort of yes and no. It was an earlier result that ended up having some of the same.
So in particular, a priori, it has nothing to do with his homotopy theoretic model structure, the one for the open.
No, it is that one. It's his homotopy type theoretic model structure. Yeah.
Okay, but then I'm confused, because if it's an open problem, that it should be because you prove only that the composite is a quillen equivalence.
Right, that's right. So
okay, I see.
Yeah. So I mean, this. Let me say a little bit about that. That's a very good point. But Martina's ahead of us. I'll finish and then catch everyone up. So
thanks.
So firstly, we have these left quillen functors. So we descend to these derived functors. And I'm going to show that the composites are inverse equivalences. So how do you do that? At the level of the homotopy category, we have these natural transformations here that descend from the unit and the co-unit upstairs. So because I was a full embedding, the unit of this adjunction, I'm wondering if that should be the co-unit. Maybe that's backwards, but no, I know the unit's well, whatever. Yeah, the unit's fine. This thing is if you left connexin and restrict, you get back to where you started. So this unit is an isomorphism. So that's definitely an isomorphism. So the final step involves proving that these three functors are weak equivalences. So this is a natural weak equivalence. This is a natural weak equivalence. This is a natural weak equivalence. This step uses Reedy techniques very, very, very heavily. So this eta is something that's defined on objects in this category of Cartesian cubes. And by Reedy stuff, we can reduce to the case where we just show that this is a component-wise weak equivalence on the cubes and the quotients of cubes by symmetries. And that just that's sort of absolutely crucial for the argument in showing this is a weak equivalence, is being able to use Reedy stuff to reduce our consideration from a general object to a cube or a cube quotient. And something similar is going on with this epsilon. I mean, here we only have to show that epsilon is a weak equivalence when we restrict along this I shriek and post-compose with I star, and similarly here. And so what that means is, in this case, we're going to be really considering objects in this category. And in this case, we're going to be considering objects in this category again. And since both of these are Reedy categories, we're allowed to reduce, in this case, to just thinking about simplices, and in this case, to thinking about cube quotients. And that's how we prove that these are the weak equivalences. So this last step is relying really heavily on the Reedy stuff. And so the summary again is that we're showing that this model structure is equivalent to this model structure by passing through the model structure where it's an open question whether it's quillen equivalent to spaces. It does kind of suggest, especially when we discover that this one's sort of equivariant as well, that this should be quillen equivalent to spaces, but the techniques we use don't prove that at all, because they really rely heavily on readiness, and we don't have access to that in the Dedekind cubes. So that's all I wanted to say. I think I'll stop there.
Okay, well, thank you very much. So please join me in thanking Emily for the talk. And we'll have some questions now, maybe.
Back to Ezra, back to uniformity. So here, the model structures were always with uniform fibrations, I guess.
So this model structure on, right. So the model structure on simplicial sets is the classical quillen.
Okay.
So nothing.
And somehow, so when you go back the other way, you pick up uniformity in the fibration. If I start, oh no, you only have left quillen functors acting on. You don't have any right quillen functors coming out of.
Well, of course you do. The right adjoints are then right quillen. So you do actually pick up some, so equivariance isn't, we do pick up sort of uniformity.
Oh, so you have a functor that creates uniformity in cubical objects starting with a Kahn complex, a Kahn fibration.
Sure, something like that, yeah.
I see, I have to learn that, yeah.
Right, so I mean, this equivariance and uniformity is meant to be reflections of properties that were already present in some way in the classical quillen model structure on simplicial sets, but maybe we weren't visible.
Yeah, okay.
Is there any relation between these type theoretic model structures on Cartesian cubical sets and Dedekind cubical sets and the test model categories?
Yeah.
Those ones coming from test categories.
Right. So that it's a bit subtle, and what I'm about to say might not work for all cubes. I don't quite remember. So, I mean, the person to ask this question to is Ulrich Buchholz. But essentially, there's a zigzag of quillen functors relating. So the triangulation functor and the map to the test model category, and then I guess you pass to model structure on cat, and then to simplicial sets. But yes, there's some diagram like that commutes at the level of homotopy categories or something like that. So it is, I'm not explaining this very well.
For instance, do they have the same weak equivalences or perhaps different weak equivalents?
Right. So I think a posteriori, what we're showing, right, so that's a good comment to make. So a posteriori, what we're showing in the case of the Cartesian cubes is that this model structure coincides with the test model structure, though it's described in a completely different way.
Okay, right, because you said the cofibrations are the monomorphisms.
Right, cofibrations are monomorphisms, both of these are equivalent to simplicial sets. So yeah, a posteriori, we're proving essentially that this is the test model structure, which we had already, which is kind of crazy. But, but in particular, you don't know that these test model structures are like, type theoretic model categories or whatever the going axiom is.
Is that open question concerning the Dedekind cubical sets maybe equivalent to saying that this type theoretically defined model structure is the same as the test model structure?
Yeah.
Sorry, Chris, I cut you off.
Oh no, I was just going to make that comment that the question for Dedekind can be rephrased in exactly this way. So rather than asking for equivalence to spaces, you just compare the two model structures and cubical sets. Both have cofibrations and monomorphisms, but it's much harder to access fibrations in the fibrations in the test category one, and weak equivalences in the type theoretic one.
Sure.
I hope I didn't say it backwards. Repeat.
No, you said it right.
That makes sense. Yeah.
I'll make a comment that Christian was also, I think this attitude of being open-minded, when we were working on Cubical's Royale thing, he kept telling me, we need to be open-minded and think that our model structure will be complete failure and it won't be equivalent to this Royale model structure. So you can see the impact of this thing on him now. Okay, any other questions or comments?
This is sort of a vague question, but we see that these different type theoretic model structures may or may not be equivalent to spaces or equivalent to the test model structure. I wonder, is there some type theoretic version of what that means for such a model?
I guess I don't know what you mean by that.
What I'm trying to get at is that, like, it would seem like being equivalent to a test model structure ought to convey something about how the model describes something about some property of the semantics in terms of the type theory. Like maybe it is more or less something by being equivalent to spaces as opposed to something else.
Right. I guess I think the language I've heard people use is that these, so the BCH model or the CCHM models are giving, there's some sort of synthetic homotopy theory of cubes, but we just don't know the homotopy theory of what, I mean, just, we don't know. Like if you compute a homotopy group in those cubical type theories, what sort of, what are you computing the homotopy group of or something?
So it's really just they're describing something other than spaces.
Right. I don't know if it's entirely known what they're describing, but I'm not really a cubical homotopy type theorist, so maybe they do know what they're describing, and I just don't know what that is. But.
So I think like this is one of the open problems where, so you know that the resulting model structure will be presenting an infinity topos, and then you know that it's not going to be a topos of spaces. So now the question is, what's the site? right? Like we know it's going to be presentable. We know a lot of things about it. And so what is the site that we're going to be using? And yeah, that's still open. For some of these model structures, they're not known to be equivalent. I'm not even sure how one would attempt to like trace back what the site is. I don't know. It seems like the construction is so convoluted. A quick comment in the chat: cubical sets are weird.
It's part of why they're so cool.
That's where we got through into the seminar. Okay. Any other questions? Comments? Okay. Well, so before we thank Emily again, I'm just going to say, and I believe I'm speaking on behalf of us all, Emily, like as the lead organizer of this special program, like we are really, really grateful for all the hard work that you've done, and thanks for bringing us all together and allowing us to participate in this. And for me, it was a great learning experience and great research experience. And I'm sure, like, again, I'm speaking on behalf of everyone here. And the fact that in the middle of all that, you still have time to give a talk for us is like just amazing. So thank you very much. So please join me in.
All right, thanks.
Thanking Emily.
Yeah, it's fun to see some homotopy type theory in this. I think it's a exciting area. So